All right, welcome. Today, we are diving into what I think is a secret weapon for sustainable design, and it's a topic you absolutely have to know for your ARE exams. I'm talking about geothermal heat pumps. We're going to break this down piece by piece so you can walk into your PPD and PDD tests feeling totally confident.
So let's just start with this one big idea. Seriously, what if the ground right underneath your building was basically a perfect free battery for all your heating and cooling? Think about that. What if you could tap into this massive, super stable energy source that's just there? That's really the core of what geothermal is all about. It's not about creating heat, it's about moving it. It's using the earth like a giant rechargeable thermal battery. It's pretty cool.
Okay, so let's get into the official definition here. A geothermal heat pump, or GHP, you'll see that a lot, is the super high efficiency system. And all it does is use the Earth's stable temperature. You see, in the winter, when it's cold outside, it pulls heat from the ground into your building. Then in the summer, when it's hot, it does the exact opposite. It dumps the heat from your building into the ground. It's just a big energy swap, and it's incredibly efficient.
All right, here's the game plan for today. We're going to start with the Earth's secret power, then meet the three main GHP systems. After that, we'll look at the big picture PPD strategy and then zoom into the nitty-gritty PD details. And stick around, because at the end, I've got an exam day cheat sheet just for you. Let's do it.
First up, the Earth's secret power. Let's get into the core concept here. The whole magic trick of geothermal really just comes down to one simple, incredibly powerful fact about our planet.
And this is the magic number, 50 to 60 degrees Fahrenheit. Once you get just a few feet below the surface, the ground stays at this almost perfectly constant temperature all year long. We're talking about 10 to 16 degrees Celsius, so think about it. When it's freezing cold outside in the winter, the ground is a relatively warm 55 degrees. And when it's a blazing hot summer day, the ground is a relatively cool 55 degrees. It's this perfect, moderate, sweet spot, always ready to either give up some heat or soak some up. That's the whole secret right there.
Okay, Section 2. Meet the three GHP systems. This is about choosing your tool. So how do we actually tap into this amazing thermal battery? Well, you've basically got three main tools in your design toolkit, and you can bet the ARE is going to test you on picking the right one for the job. So let's meet them.
First up, we have System 1, the horizontal closed loop. I want you to think of this one as the wide and shallow option. It's kind of like the sprawling, budget-friendly member of the GHP family. It needs a lot of personal space, a big backyard to spread out in. What we're doing here is basically digging trenches, maybe 4 to 6 feet deep, and just laying coils of pipe flat in the ground.
So what are the trade-offs? Well, the big pro here is cost. It's usually the cheapest one to install, mainly because you can just use a regular excavator, no fancy drilling rig needed. But the cons, well, they're big. Literally, you need a huge amount of land, which makes this a total non-starter for most urban projects. You're also tearing up a lot of the landscape. So for the exam, listen up. If you see the words rural, large site, or big yard, your brain needs to go straight to horizontal loop. That's your clue. Okay, System 2 is the vertical closed loop. This is the narrow and deep one. If the horizontal was the country cousin, this is the sophisticated city dweller. It's super compact, really efficient, and it can fit just about anywhere. I mean, literally under a building or a parking lot. Instead of digging wide, we're drilling deep. We're talking hundreds of feet, straight down, and then we drop these U-shaped pipes into the boreholes. And right here, this is your solution for tight urban sites. The biggest pro by far is its tiny footprint. You can squeeze this system onto almost any property. Plus, since you're drilling way down deep, you're tapping into those super stable earth temperatures, which actually makes it even more efficient. So, what's the catch? The cost. It costs a lot more upfront because you need a big specialized drilling rig to do the work. So on exam day, if the prompt says urban, small lot, or limited space, ding, 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 vertical loop is almost always your answer.
And last but not least, System 3, the open loop. This one is the wild card. It's direct, but it's also risky. See, this system doesn't circulate fluid in a closed loop of pipe like the others. Instead, it literally pumps groundwater up from a well, runs it through the heat pump, and then dumps it back into the ground. It's a high-performance, high-risk play that needs everything to be just perfect.
So here's the deal with this one. The pro is that it can be insanely efficient. I mean, water is a way better heat conductor than the antifreeze solution in the closed loops. But, and this is a huge but, it comes with major risks. The water quality can wreak havoc on your pipes, causing corrosion and scaling. And there are tons of code restrictions because you're messing with the local groundwater and nobody wants contamination. So here's the exam tip. This is very often the distractor answer, the trick answer.
You should only even think about choosing this if the question practically screams at you that there's abundant clean groundwater and that local code's permitted. Otherwise, stay away. All right, let's switch gears a little. Section 3, the PPD strategy. We're talking big picture system selection. This is all about your PPD exam, project planning and design. At this early stage, it's all about strategy. It's about looking at the big picture and making the right call from the get-go.
This slide perfectly shows the two different hats you have to wear for these exams. For PPD, you're the planner, the strategist. You're asking the big questions. Which system even makes sense for this site? What's the initial cost versus the lifecycle cost? But for PDD, you put on your builder hat. You're down in the details, the nitty-gritty. How do we actually build this? What pipe material do I specify? What does that grout detail look like? Two totally different mindsets.
Okay, this is a classic PPD concept. Initial cost versus lifecycle cost. And this chart tells a really important story. Look at that initial cost for geothermal. It's high, way higher than a traditional HVAC system. That's a tough sell sometimes. But then look what happens over the life of the building. The lifecycle cost is way lower. Why? Because you're only paying a little bit of electricity to move heat around, not a ton of money to burn fuel to create it. That gap between the initial cost and the long-term savings, that's your payback period. And that is a key concept for PPD.
So when you're in that PPD mindset, here's your mental checklist. These are the questions you have to ask. Is the site huge and out in the country? Okay, let's consider a horizontal loop. Is it a tiny lot in the middle of a city? Vertical is probably our only play. Do we have this magical unicorn situation with a giant, clean aquifer and friendly codes? Maybe we can look at an open loop, but we're going to be careful. And one more thing, is the heating load pretty balanced with the cooling load over the year? That's really important for keeping the ground temperature stable long term. Okay, time to switch hats. We're moving on to Section 4, the PD details. This is the nitty-gritty of construction. For your project development and documentation exam, the question isn't what do we choose, it's how do we build it. We got to specify the right parts and pieces to make sure this thing actually works and doesn't fail in 10 years. Now, these are the specific details that can and will show up on your PDD exam. You need to know this stuff. The pipes, they're going to be high-density polyethylene, HDP. That's the standard. The joints, you can't just glue them. No way. They have to be heat fusion welded. That's what makes a perfect, seamless, leak-proof seal for 50 years. And for those vertical loops, that bentonite grout that fills the borehole, absolutely critical. It's for good thermal transfer and for protecting the groundwater. You also have to think about how those pipes actually get into the building. Coordinating that penetration detail is key. These are the terms you'll see in specs and on drawings. And our final section, your exam day cheat sheet. Okay, we have covered a ton of ground, pun intended. So get ready. This next slide is the one you're going to want to screenshot. This is your final summary to pull everything together before you walk into that exam.
Let's just do a lightning round through this. Site needs: horizontal, big and rural; vertical, small and urban; open loop, that perfect groundwater source. Got it? Initial cost: horizontal is low to medium; vertical is high. Simple. Efficiency: horizontal is good, vertical is very good, and open loop is the highest, if it's a viable option. And finally, the most important part, the HER context. Think of it this way. Horizontal is your budget and space option. Vertical is your performance option. And open loop, that's your high-risk distractor answer. Know the difference.
So there you have it. That's the full breakdown of geothermal heat pumps, soup to nuts, for your ARE exams. You've got the science, you know the three systems, and you know how to switch between that PPD big picture thinking and PDD detailed thinking. The only question left is the one on the screen. For your next project, real or just for the exam, which ground loop are you going to choose? You've got the knowledge now. Thanks for tuning in. Good luck on those exams.